And we thought of graphene oxide being a material that can be used as a compatibilizer. We can tune up the content of the oxygen groups on the surface and then the surface energy. And by that, we can drive it to the interface of a miscible polymer blend and try to use it as a compatibilizer. So by using graphene oxide instead of graphene, which is something that has been tried in the past, we're losing some of the properties, a little bit of mechanical properties. We lose the conductivity, the electrical conductivity, but we keep many of the other properties that we need, like permeability or low permeability to gases and liquids. And we can tune up the surface energy. We start with the high surface energy, and we can modify it by introducing functional groups on the surface. Now, this has been tried in a series of papers done in other places. For instance, polyamide and PVDF. You can see in these pictures here how the domains of the PVDFs are being reduced in size by introducing graphene oxide to the blend. So the objectives of this work are to study graphene oxide and its modifications as a compatibilizer for polyamide, polypropylene blend systems as a model system, and investigate the possibility to control the localization of graphene oxide. Basically, I would like to localize graphene oxide at the interface, and by that, by using a very small quantity of graphene oxide, we would be able to tune up the properties of this system. So we are going to do that by managing the oxidation level of the graphene oxide, and we're going to keep the ratio of the polypropylene and the polyamide constant, just in order to simplify things. So what we do, basically, we oxidize commercial graphite to graphene oxide, and then we modify it with surfactants, or if you wish, silanes. We're using a low energy silanes, such as amine silane, aminosilane, and octyl silane, or hydroxyl alkyl silanes, the kind of silanes that give you low surface energy. Now, to control the morphology of the system, we're going to look at two things. One is the thermodynamics of the system through the wetting coefficient, okay, and we want to get somewhere there where the wetting coefficient is basically zero. Okay, the other thing we want to control is the kinetics. That means the time we are going to process the system in order to allow the graphene oxide to move or diffuse into the interface. So we did some calculations based on the Owens-Wendt model, and we find that if we mix graphene oxide with this system, it's going to be located in the polypropylene. That's because of the surface area of the graphene oxide. That's not what we want. So in order to modify that, we're going to use, as I said, modifiers. For instance, aminosilane, which is the one I'm going to show you results today. Okay, I can show you that by modifying the graphene oxide with the silane, we get better thermal resistance. This is a TGA showing how the material reduces, degrades with temperature, with graphene oxide and modified with aminosilane. The results are better. This is a differential graph that shows you the lower change in weight by modifying the surface. We did the kinetics study as well, seeing how time affects the change in morphology, so that from phase separated systems where the graphene oxide is all over or in the polypropylene at the beginning, after something like 15 minutes, we get it at the interface. This is what we wanted. We checked also the mechanical properties because, as I said, we need both reinforcement and reinforcement and compatibilization. And we see that there is enhancement in mechanical properties, which is nice to have. I mean, we need both properties to be enhanced. So this is the summary. I will leave you with it. Thank you very much.